Welcome, curious minds, to another deep dive. Today, we're pulling back the curtain on a segment of the global economy that, well, you might not think about often, but it's absolutely crucial. It impacts products you use every single day. We're talking about the global plastic injection molding simulation software market. Our mission for this deep dive, we've got a pretty comprehensive market report for 2025, and we're going to unpack it. We'll sift through the data, the insights, try to get beyond just the numbers and understand what's really driving things in this rapidly expanding field.
Yeah, and what's truly fascinating here, I think, is how this, specialized technology is becoming so indispensable. It's not just about making plastic parts cheaper, although that's part of it.
Yeah.
It's really about making them with incredible precision,
Mm-hmm.
predicting problems, defects before they even happen, and drastically speeding up how quickly new products get developed. It affects everything. I mean, from tiny medical devices to, big automotive components.
Okay, so let's kick things off with that big picture then. The growth sounds pretty impressive.
Oh, it is. Serious expansion. Back in 2021, the market was valued at roughly $830 million.
Okay, $830 million.
Right. But get this, by 2025, it's projected to jump to over $1.2 billion.
Wow.
And the forecast out to 2033, it's looking like a staggering $2.55 billion.
$2.5 billion.
Yeah. We're looking at a compound annual growth rate, the CAGR, of nearly 10% over that whole period.
Almost 10%.
Yeah.
That's not just steady growth. That sounds like an industry really transforming itself.
Exactly. It's fundamental change.
So, okay, beyond these big numbers, what does this actually tell us? What are the specific forces, pushing this kind of rapid, sustained growth in something so specific?
Well, this kind of growth, it really signals a massive shift in how manufacturing gets done. Traditionally, making, say, a new plastic part involved a lot of trial and error, right? You design a mold, you make physical prototypes, you test them, you find flaws, maybe it warps, or you get sink marks.
Right, the classic problems.
Exactly. And then you go back, redesign the mold, make another prototype. Each cycle costs a ton of money and, crucially, time.
Okay.
This software, it eliminates so much of that guesswork. It lets companies basically inject molten plastic into a digital version of the mold virtually. It simulates the whole process, how the plastic flows, how it cools down to, almost a molecular level.
So you can see the problems before they happen.
Precisely.
Yeah.
You can predict defects, stresses, warpage, all of that before you cut a single piece of metal for the actual physical mold. It's like having a digital prototyping lab. It saves companies, immense resources, and it just slashes the time it takes to get a product to market.
That makes perfect sense. You're anticipating problems before they become these expensive, time-consuming realities. Okay, let's try and unpack this growth globally now. Where are we seeing the biggest jumps, the most significant acceleration? What does that tell us about maybe industrial shifts happening around the world?
Yeah, connecting it to the bigger picture is key. It definitely shows how different regions are adopting these advanced manufacturing tools at different paces. Right now, North America is leading the market. It's expanding from around $280 million back in 2021
Okay.
to a projected $831 million by 2033.
Big jump.
Huge jump. And within North America, the United States is still the largest contributor by far. Canada is also showing very strong, robust growth.
Interesting. And how does Europe stack up against that? Are we seeing similar kinds of trends and adoption over there?
Europe's market is definitely expanding, quite steadily, actually. It's projected to nearly triple. It started around $188 million in 2021, and the forecast is over $550 million by 2033.
Still significant growth.
Very significant. Germany, as a manufacturing powerhouse, is leading the way there. But the UK is also showing really impressive acceleration. Its CAGR is actually over 10%.
Oh, wow. Higher than the global average.
A bit higher, yes.
Mm.
And what's also kind of noteworthy is the significant growth in what the report calls the rest of Europe.
Mm.
It suggests this technology is being adopted quite broadly now, beyond just the traditional industrial giants.
Okay. Now let's shift our gaze, maybe, eastward. Asia Pacific, often called the global manufacturing heartland. Is it living up to that reputation in this specific software market?
Oh, absolutely. Asia Pacific is definitely one of the fastest growing regions for this software. It's projected to grow from roughly $141 million in 2021 to almost $473 million by 2033. That's a strong CAGR too, but 10.5%.
Okay, so right up there.
Yeah. China, as you'd probably expect, leads the region in terms of overall market size. Huge internal market, huge manufacturing base.
Makes sense.
But here's where it gets really interesting, I think. Taiwan.
Taiwan, okay.
Despite being a smaller market overall compared to China or Japan, Taiwan actually boasts the highest growth rate. not just in Asia, but across all the regions we've looked at so far. Its CAGR is projected at over 13%. Remarkable.
13%. Wow. What does that signal?
Well, it suggests it's not just about general adoption. It really points towards Taiwan's strategic focus on, high-value, high-precision manufacturing. Think about demanding sectors like advanced electronics, medical devices, areas where getting those plastic components absolutely perfect, flawless, is critical. They seem to be heavily investing in these simulation tools.
That is a fascinating insight. It's about strategic adoption for specific industrial strengths.
Okay, so beyond these, let's call them the major players, what's happening in other emerging markets? Thinking South America, the Middle East, Africa. Are they catching on to this simulation trend with the same kind of vigor?
They are, absolutely.
Mhm.
Maybe starting from smaller bases, but the growth is there. South America, for instance, is on a steady expansion path. It's on track to nearly triple its market size by 2033 as well. Brazil is the dominant force there.
Uh,
The Middle East is actually one of the fastest growing regions globally. Its CAGR is pegged at 11.1%.
Faster than North America or Europe?
Yep, one of the highest KGRs overall.
Mm.
Saudi Arabia and the UAE are the clear frontrunners, which points to, significant investment in diversifying their economies and boosting advanced manufacturing capabilities.
Interesting. And Africa?
Africa is also gaining momentum, growing at a healthy 9.6% CAGR, very close to the global average. It's projected to grow from about $61 million in 2021 to over $190 million by 2033, led by countries like Nigeria and South Africa. So listening to all this, what does it really mean for you, the listener, looking at these global technology trends? It feels like this isn't just about some niche software anymore. It seems like it's a reflection, a really profound one, of a global push for efficiency, for precision, for innovation, and how we make almost everything.
Precisely. That's the key takeaway, I think. This deep dive, it really shows this rapidly growing global demand for advanced simulation tools. It's being driven by these universal needs in manufacturing. Optimize the process, cut costs, reduce waste, and just handle the increasing complexity of making things, especially with plastic injection molding. And each region, as we saw, it showcases its own unique growth story, reflecting different stages of industrial expansion and technology adoption. But the core driver is the same. This isn't just about making things anymore. It's about making things smarter, making them with fewer errors, getting them right the first time, and doing it significantly faster. We're seeing companies really invest heavily in these predictive analytics, to avoid those costly physical prototypes and ensure the quality is baked in from the very first virtual run.
What an incredible journey through this often unseen corner of the global economy from, what was it, $830 million just a few years ago to a forecast of over $2.5 billion in just over a decade. The growth of plastic injection molding simulation software is, well, it's truly remarkable and so globally distributed, too.
It really highlights just how critical these specialized tech tools are becoming for industries everywhere. That shift towards greater precision, towards reducing waste, which is huge environmentally and economically, and speeding up innovation. It's a universal driver now. And this market report, it just underscores that perfectly. It really is about optimizing every single step, transforming manufacturing from maybe an art based on experience into more of a predictive science.
So let's leave our listeners with something to chew on after this deep dive, a provocative thought perhaps. If simulation software is so fundamentally changing how we design and create something like plastic components, what other industries, maybe ones that seem mundane or even incredibly complex, are ripe for a similar digital transformation? Think beyond manufacturing, maybe areas you wouldn't normally expect, like, I don't know, food production, construction, even fashion design. How might that kind of simulation-driven approach impact the products, the services, the environments you encounter every single day? Something to think about.
Welcome to the Deep Dive, where we take a stack of your sources and extract the most important nuggets of knowledge. Today, we're diving into a fascinating area. It's right at the crossroads of manufacturing efficiency, digital innovation, and engineering precision. We're talking about the world of plastic injection molding simulation software. Imagine that perfectly smooth, lightweight plastic case for your phone, or maybe a tiny, precise part in a medical device. You probably don't think much about the hidden battles fought to make them flawless. So today, we're unpacking the software that makes those battles winnable. By the end, you'll have a much clearer picture of how this often unseen technology shapes the products you use every single day.
Yeah, and what's really remarkable here is how absolutely critical this software has become, especially for industries really aiming for perfection. We're going to explore, the key forces driving its adoption, the significant hurdles it still faces, and some pretty cutting-edge trends that are genuinely reshaping modern manufacturing right now.
Okay, let's unpack this then. Our sources highlight a major reason for the huge growth of this software. It's this rising demand for flawless economical mold designs. So when we say flawless design, what specifically does this software let manufacturers do that was maybe so hard before?
Right. That demand for perfection, that's really the core driver. It's why this market is just exploding. You see manufacturers across, well, tons of industries, automotive, electronics, packaging.
Even medical devices you mentioned.
Oh, absolutely. Highly sensitive medical devices, too. They're all increasingly relying on the simulation software. And the big reason is it allows them to predict and basically eliminate potential defects before they even make a physical prototype.
Okay, so predicting problems. What kind of defects are we talking about?
We're talking critical flaws, things like air traps, those tiny bubbles that can, weaken the plastic from the inside, or weld lines where the molten plastic flows meet up. They often create visible seams, sometimes fragile ones. It even anticipates warpage.
Warpage, like the part bending out of shape.
Exactly, where parts deform as they cool. That's critical for dimensional accuracy and making sure everything fits together correctly later. What's really revolutionary here isn't just the speed, though that's part of it. It's the ability to virtually fail thousands of times in minutes, catching defects that otherwise could cost manufacturers millions.
Millions in wasted prototypes or even recalls down the line.
Precisely. It's like redefining failure as foresight. You see it coming.
And this whole process, it doesn't exist in isolation, right? It seems deeply connected to the bigger shift towards digital tools in manufacturing. How does this simulation software connect with, say, 3D CAD systems or digital twins? What does that integration unlock?
That's a great point. Placing it in context, these simulation platforms, they integrate pretty seamlessly with 3D CAD systems and with digital twin environments too, which are essentially virtual copies of a physical product or process.
Okay, a virtual replica.
Right. And this integration allows for incredibly early validation of the mold designs. As digital manufacturing and, product lifecycle management keep evolving, these tools just become indispensable. They help different teams talk to each other, collaborate better. They minimize design errors and ensure that tooling precision right from the very first concept.
All the way to completion.
All the way through, yeah.
And it sounds like it's not just about standard everyday plastic parts either. We're seeing these tools used more and more in highly specialized areas,
Yeah.
particularly for really lightweight and complex parts.
Absolutely. Think about the aerospace sector or automotive, especially with electric vehicles.
Right, where weight is everything.
Exactly. Take a critical component for a new EV, maybe the structural casing for a battery pack. It needs to be incredibly light, but also strong enough to handle impacts, protect those high voltage cells. As these industries shift towards high-performance polymers and really intricate part shapes, simulation becomes non-negotiable.
So it helps them understand things they couldn't easily see before.
Precisely. It helps engineers deeply understand complex things, like how the molten plastic actually flows inside the mold, or temperature distribution during cooling, and how effective the cooling channels are. These insights let them produce highly accurate, lightweight plastic parts with, frankly, far fewer design iterations.
And less risk in production.
Significantly lower production risk. It's almost like having X-ray vision into the manufacturing process before you even cut the first piece of steel for the hold.
But like any powerful tech, it's not all smooth sailing, is it? It doesn't come without hurdles. Our sources definitely mention some significant challenges this market faces. If a manufacturer is looking to adopt this, what are some of the biggest barriers stopping wider adoption?
Yeah, that raises a really important question, especially for, say, smaller businesses. One major barrier is, without a doubt, the high cost. Both the software licenses and the specialized training needed to use it effectively.
Wow, the cost.
Yeah. While, large enterprises can usually absorb these expenses, small and mid-sized manufacturers often find that upfront investment pretty tough to justify, especially if they're already dealing with tight budgets or maybe don't have a dedicated team with the right technical skills.
So it's not just the initial price tag then. It sounds like there's also the complexity of the software itself, and then finding the right people. That seems like a pretty significant hurdle, especially for smaller shops trying to get on board.
It really is. And another technical limitation involves just the sheer complexity of accurately modeling real-world conditions. I mean, even with all the advancements in how accurate simulation is.
Not perfect.
Well, real production environments often vary. You have factors like slight machine tolerances, maybe small inconsistencies in the raw plastic material batches, or even just environmental changes on the factory floor, temperature, humidity. These variables can create differences between what the simulation predicts and what actually happens.
Which could undermine trust in the software, I imagine.
Understandably, yeah, it can reduce trust in the predictive reliability. And yes, as you mentioned, there's also a limited pool of skilled professionals, people proficient in thermoplastics, fluid dynamics, and simulation-based engineering. Many organizations really struggle to recruit or train people who can use these sophisticated tools to their full potential. That definitely hampers wider adoption, too.
Okay, so challenges around cost, complexity, real-world accuracy, and skills. But looking ahead, despite these issues, our sources highlight several powerful trends that are helping reshape the landscape, maybe pushing past some of these barriers. What are some of the most exciting developments we're seeing now?
What's compelling here is how the market is genuinely adapting and innovating. It's not standing still. One really powerful trend is the growing integration of cloud computing and AI-based optimization directly into these simulation platforms.
AI. How does AI help here?
Well, imagine AI algorithms actually assisting engineers, maybe suggesting design improvements based on simulation results, or even automating entire simulation loops, running variations, learning, suggesting speeding up that whole trial and error process dramatically. And cloud-based platforms, they offer scalable computing
So
resources.
you don't need a supercomputer in-house anymore.
Right. And collaboration tools, too. It's perfect for teams spread out geographically, working on rapid prototyping, agile development. It definitely levels the playing field somewhat, giving more companies access to serious computing power.
That makes sense. And what about sustainability? With the global focus on environmental impact, corporate responsibility. That playing a role here too?
Oh, it's absolutely becoming a core focus now. It's not just a nice to have. Manufacturers are increasingly using simulation specifically to optimize how much material they use, also to significantly reduce cooling time, which directly saves energy, and to minimize scrap rates, less waste.
So tangible benefits for the environment and the bottom line.
Exactly. These capabilities are vital for aligning with corporate ESG targets, environmental, social, governance goals, and broader environmental mandates. You see this especially in consumer goods and automotive sectors. They're really trying to shrink their carbon footprints, adopt circular economy principles. Simulation is a direct path towards that.
Okay, that's a huge driver. Finally, the world of plastic injection molding itself isn't static, is it? Especially with demand for even smaller, more precise components, like that tiny medical device part we talked about earlier.
Exactly right. The emergence of multi-material molding, where you combine different plastics in one part, and microinjection molding is driving significant software evolution.
Microinjection, so really tiny parts.
Extremely tiny, yes. As demand grows for complex electronic components, things that go into wearables or sensors and ultra-precise medical devices, the simulation software is advancing rapidly to handle these intricate processes. There are new modules now that let engineers assess complex material interactions, predict minuscule amounts of shrinkage, and ensure dimensional accuracy even at microscopic levels. It's really unlocking the potential of true precision manufacturing.
It really shows how deeply embedded this technology is becoming, doesn't it? In cutting-edge product development across so many different fields.
Absolutely. It highlights how often behind the scenes, these precision tools are constantly evolving. They have to meet the demands for faster, better, and increasingly more sustainable products that we all rely on every day.
You know, thinking about this deep dive, it's clear this isn't just some niche engineering tool anymore. Hearing about its role in lightweighting for aerospace, enabling microinjection for medical tech, it really feels like a foundational piece of tomorrow's manufacturing.
It really does. It's enabling innovation in ways that weren't possible even a decade ago.
And for you, our listener, what this deep dive hopefully underscores is how a seemingly specialized tool like this isn't just optimizing a single process. It's truly a foundational pillar of the broader digital transformation and manufacturing, quietly enabling innovation across entire industries. So next time you pick up that sleek smartphone or think about advanced medical tech, consider where plastic injection molding simulation software might have played its hidden, crucial role. Where did it help turn a complex concept into that physical reality in your hands? Keep those questions in mind. Thanks for taking this deep dive with us.